power. So first physical quantity is what, right? So we understood that, let's say we have some force acting on that object,
Sir,
and yes,
maybe this is extra class.
no, this is not the exact. Why? I'm going ahead.
I,
Yeah, so I'm going.
I missed one or two class because of Quran classes. Yeah, I remember now.
Oh, so when I started this work energy and power, you were not there.
No, no, sir.
Oh,
Actually, it was my time for Quran class, so I didn't join.
okay. So yeah, so then we can. Good. So then we can revise this portion, right? So what I
Yes, sir.
did, yeah, good. So then it's okay. So what I did in the previous class, right? So I started this chapter which is work, energy, and power, right? So in the chapter before, we understood about what? What is the physical quantity that we understood in the previous chapter in laws of motion? Yeah.
We studied about friction. We studied about equilibrium.
Yeah, so we found out or we studied about the force, right?
Yes, sir.
So we studied that how this force comes into existence, right?
Yes,
So
sir.
and and in this chapter we will learn that what is the implication of that force, right? What is the product of that force, right? So the first thing is about this work. And yeah, so in our daily routine, whenever, let's say, a painter is painting something, right? Painting some portrait, or let's say you are writing your homework, right? Or let's say that a laborer is doing some work, right? So
Yes, sir.
all those things that a painter is doing his work, you archive, you are writing something, which means that archive you are doing your work, and laborer is also doing some work, right? But in the
Yes, sir.
physics sense, what is the thing? What is the actual definition of the work, right? Those people are all doing some work. But in physics sense of view, what is the definition of this work? So in this chapter, we will learn about what is the physical significance of work, energy, and power, right?
Yes, sir.
Okay, so first thing that we learned was this work. What is the work? So to learn, to study about this work, we have to go back in the vector classes. So in the vector classes, we learned about the products of two vectors, right?
Yes,
So
sir. Cross product and dot product.
absolutely right. So whenever we are taking a product of two vectors and are getting another vector, so that product is called.
Sorry, sir.
So I am multiplying or I am taking the product of two vectors and I am getting another vector. So what is that product called?
Dot product.
Dot product. So if you multiply two vectors and you get a vector, then you call that a dot product. Hmm. So
Scalar product.
scalar product, right? Because you are getting a number. So okay, so let's say you are multiplying, let's say A and you are multiplying you are multiplying two vectors A and B, and you are getting a C vector. So this would be called vector product, right?
Yes, sir.
Because you are getting another vector, so this is called vector product. But when you multiply two vectors and you get a number, let's say constant number k, so then this is what? This is a scalar product, right? Because you are not getting any other vector, right? You are
Yes, sir.
getting a scalar number. So that is why this is called a scalar product. So this dot product is a scalar product,
Yes, sir.
right? And then this cross product is a vector product, right?
Yes, sir.
So this we learned in the vector classes, and then how do we represent this scalar product? So we have two vectors A and B, and A dot B is defined as AB cos theta, right? This we have done.
Yes, sir.
So where is this scalar product is used? So it is used in calculating the angle between the vectors. It is used to calculate the work done and power, and it is also used to calculate projection of vectors, right?
Yes, sir.
So do you remember what is the projection of vectors? So let's say you have this vector v, and this is let's say theta. So what is the uh, if you project this vector in this direction, so what is this part, horizontal part?
Sin theta. V
Horizontal is,
sin theta.
this is v sine theta,
V cos theta. Cos theta. Sorry.
v cos theta, right? So v cos theta. So this is v cos theta, and what is this part?
V sin theta.
V sine theta, right? So good. So this is called the resolution of vectors, right? So I have what is a projection of vectors. This we have done in the dot product. So I have two vectors, right? Two vectors making an angle. So let's say this is A vector and this is B vector. And the angle between these vector is theta, right? So let me bring the, okay. So I have two vectors, right? Making an angle theta with each other. So this is
Yes,
my
sir.
A vector and this is my B vector, right? So the
Yes,
projection
sir.
of vector means that let's say this is my B vector. I project it along A vector. So if this is B vector, what is this component of B vector called? Yes,
Component of B vector.
yeah. So this is B. What is this component?
Sir, it will be 0.
This is B, and this is. I'm not asking about the angle between this and this. I'm saying that this is my B vector, right? This is my B vector. So what is
Yes, sir.
this component?
Sin
This
theta.
is my cos theta, right? Cos theta.
I-
So
Okay, sir. Cos theta.
this is B vector, right? This is
Yes, sir.
B vector, and if I take in here, so this is B cos theta, right?
Yes, sir.
So this B cos, if I take the projection of this B, and this is B cos theta, so this will be called, B cos theta will be called the projection of B vector along A direction, right? So this B cos theta is projection of B along A. Understood?
Yes, sir.
This we have already learned in the vector portion. So, and this was the dot product that we calculated, right? So this is A vector and magnitude is what? This is the magnitude. AX square, AY
A
square,
x
AZ.
square plus ay square plus az square.
Yeah.
It will be in
So
whole bracket.
yeah. So root of this. So this is how we calculated the magnitude of vector, and a dot product would be this, right? So
Yes,
if
sir.
you have, yeah, because only I dot I is 1 and I dot j will be 0, I dot k will be 0. This we have done already, right? That is why I'm not
Yes,
repeating
sir.
it. Okay, so A dot B is simply AX, BX, AY, BY, AZ, BZ, right? So yeah, so A, because let's say if A is 3I plus 4j plus 5k, and B is 2I plus 3j plus 4k. So what would be A dot B, Akif? Quickly tell me this. We have done it so many
Sir,
times.
6 I cap.
I, A dot B would be vector or scalar,
A dot B will be scalar.
right? So if you are saying that 6 I cap meaning that it is a vector, right? You are giving a direction,
Yes, it will be 6 plus 12 plus 20.
right? So this would be 18 plus 20, so 36.
36. No, 38.
So A dot B. So similarly, AX, BX, AY, BY is. So this is what it is telling, right? This formula is, this is how we calculate the dot product.
Yes, sir.
And we represent a vector, right? So we represent a vector in the form of magnitude and direction, right? So if
Yes, sir.
geometrical representation of a vector is this ray. So let's say this is a vector. So this arrow part will show that the direction E hat. And this length of the arrow will show what? Magnitude, right?
Magnitude. Yes, sir.
So let's say that the projection of B vector along A. So this is my B vector, right? This is my B vector, this is my A vector. So if I take the projection of B along A, so this would be B cos theta and direction would be what?
A.
Right? Because this is in the A direction. So direction of A is A hat. So B cos theta A hat would be projection of B along A. Similarly, if I take the projection of A, right? So I drop down this A vector in B direction. And this would be A cos theta, right?
Yes, sir.
And direction would be what?
Sir, why not B hat?
Why not B hat?
Yes, sir.
So
Why
I am,
only A cos theta?
yeah, A cos theta and direction would be B hat. Yeah, you are right. So A cos theta and direction would be B hat. So this is the projection of A along B. Yeah, you are absolutely right. So if I take projection of B along A, so that would be B cos theta A hat, right? And if I
Yes,
take
sir.
projection of A along B, which means B hat direction and magnitude is A cos theta, right? So this we did in the projection part. And then we understood about, yeah, and we also calculated that, let's say we have this A vector. So what would be A dot A? And we found out that this would be A square, magnitude square. Understood?
Yes, sir.
This you can see from here. So A dot A would be AX into AX, AY into
Yes,
AY,
sir.
AZ
Understood.
into. So this would be A square. And then we talked about this definition, physical definition of what, right? So you have an object and you displaced this object by applying some force, right? So now in this chapter, we will see that what are the implication
Yes,
of
sir.
these applied force. So we are applying the force in this direction, right? And this will displace this object in here. So let's say this is the displacement. Okay, this is the displacement, and the work
Yes,
is,
sir.
this is defined as like that. This is the product of, so the projection of F along displacement. So how much would be that? Projection of F along D, how much that it would be?
F D cos theta.
F cos theta, projection of F along D, right? Or component of force along displacement. So that would be F cos theta, right?
Yes, sir.
So component of F along D. So that is F cos theta. So work is defined as the component of force along displacement multiplied by the displacement, right? So this
Yes,
is
sir.
what you call the work done. So this will come out to be FD cos theta. So can you identify this? What is this FD cos theta? What is this FD cos theta?
Sir, like how
Yeah. So
dot product or
yeah,
scalar
yeah,
product?
absolutely. So this is what I was asking. That whenever you have something like this term, AB cos theta. So what is this? This is the dot product, right?
Yes, sir.
So as I was saying that work done is defined like the product of the component of force along displacement and the displacement. So when you multiply this F cos theta into D, so you'll get FD cos theta. And this is the definition of the dot product. So work done is the dot product of force and displacement. Understood?
Yes, sir.
So this is how this work done is defined, right? And then from this relation, you can see that work is dependent upon force, displacement, and the angle between force and displacement, right? Understood?
Yes, sir.
So if your force is zero, then work done
Yes, sir.
would be
Understood.
zero. So if your force is zero, work done would be zero. If your displacement, right? If you are applying some force on a wall, right? You are, let's say, you are applying a very large force on the wall, right? But you are actually applying the force. But is the wall moving?
No, sir.
So you are exhausting so much energy of yours, but the wall is not moving. So in the physical sense, we will say that you are not doing any work, right?
Yes, sir.
Why? Because why is that?
Sir, because there is no displacement.
Absolutely right. So yeah, I have a message that yeah, because they're absolutely right. Good. So because displacement is zero. So whenever displacement is zero, work would be zero, right?
Yes, sir.
And the next thing is that let's say your force and displacement are in perpendicular direction, right? So let's say that the displacement is this and the applied force is this, right? So F dot D would be how much? So your theta is 90, right? F and D are
Cos
perpendicular.
90.
So cos
Sir,
90, which
0.
so absolutely right. So whenever your force and displacement are perpendicular, then work done would be zero. Understood?
Yes, sir.
And the next thing we learn from this definition is that this cos theta, so theta could be 0 to 80, right? So if your cos theta is from 0 to 90, work done would be positive. But let's say your force and displacement are making an angle of 180. Then this would be minus 1, right? Cos theta would be minus 1 because cos 180 is how much? Cos pi, which is cos 180. So this is minus 1, right?
Yes, sir.
So then this work would be negative. So work done can be negative or positive depending upon the angle. Understood?
Yes, sir.
So this was the definition of the work that we did. And we also saw that work is dot product, scalar product. So what would be the physical quantity? It would be a scalar quantity,
Scalar quantity.
right?
Yes, sir.
And we know that work is Fs cos theta, right? So the unit of force is Newton, distance is meter. So your work done would be Newton meter, right? SI unit is Newton meter, or you can represent it by joules. Understood?
Yes, sir.
And the dimensional formula of work is this. So can you tell me how will you get this dimensional formula? Yeah. So
Work,
yeah,
can we
work.
write F, acceleration is applied A?
Yeah. So F is ma, right?
Yes, sir.
And this is F. So m is m. Acceleration is length lt minus two. This is acceleration, right?
Sir, how
And
-2 came?
so what is acceleration? Acceleration is meter per second square, right? Unit of acceleration.
Yes, sir.
So meter is length, second is time. So t minus 2. Understood?
Yeah, okay. Yes, sir.
Or you can also see it in this way. So your acceleration is rate of change of velocity, right? dv by dt. So
Yes, sir.
velocity is length by time, right? And
Yes, sir.
time is time, so this would be length t minus t, so t minus t. So whatever method you apply, you will get lt minus t, right?
Yes, sir.
So this is mass is m, acceleration is lt minus 2, and displacement is how much? L, right? So this would
Yes, sir.
be ml square t minus 2. So that is how you will get the dimensional formula of work done. Okay.
Yes, sir.
So we understood about the implication of force, right? So let's say a force is applied and then there is some displacement. So we defined the work done. The work done was the scalar product of force and displacement, right? Okay.
Yes, sir.
So then we did this problem. So you please do this problem, right? You have an object which is applied by this 20 Newton force at an angle of 60 degrees and it moved 3 meters. So find the work done by the applied force, right? Please find this and yeah, tell me the answer.
Okay, sir.
Because from half an hour I was talking. So okay, you please do this calculation and tell.
Okay, sir. Sir, 30 joule by
Thir-
meter.
30 joules. 30 joules, right? So this is okay. So this is or not. So you can write 30 joules or you can write a Newton meter. Both are okay. So yeah, you got
Okay.
30 joules, right? So Rishita had got this 30 joules around 60 and after. So I will write your name in here, right? So Akib also got 30 joules. Good. Now let's change the question like this. So you have that you have this question. Please find the work done in here also.
And the second question, sir.
Yeah, in the second question, this one.
Okay, sir.
This one.
Sir, is it 29?
29. Okay, so let us see. 29. Good. Good, Akib. So, okay. Now let us change the question a bit, right? Now this is
Yes, sir.
the question. Good. So you remember the vector classes. Good.
Yes, sir. Sir, please can you give your hint?
So hint is written beside here, right? What is the work done? Force
Sir, F
dot product of
dot S.
displacement. And displacement is AB, right? So
Yes, sir.
AB, this is whenever you go from one point to B point in the vector class, this is how you calculate the distance, right? Displacement vector.
Yes, sir.
So this was the right. Use this and tell me the answer.
Okay, sir.
Yeah, yeah. So please try this, and whenever you face any problems, try this, right?
Sir, I got 3 I cap plus 2 J cap plus K cap. Now I'm finding work done.
Yeah, I cap plus 2j cap plus, yeah. So you are correct. Now we have to find out good. So now you have to find out the work.
Yes, sir. Sir, 17?
17. Okay. Yes, good. So 17 joules it is, right?
Yes, sir.
Good. Good, good. So you have done all the numericals by yourself. Good, Akif.
Yes, sir.
Okay.
Thank you, sir.
So, okay. MashaAllah, MashaAllah. Okay. So now we understood about, so we were calculating the work done. So in all these three forces that you calculated the work done, right? So in here, the force was 20 Newton, right? In here,
Yes,
the
sir.
in here the force is a kind of like this, and in here this force is again kind of like this. So in all these three cases, your force is constant, right?
Yes, sir.
So F is let's say 3I plus 2J plus 5K, or let's say F is 5I plus 2J, right? Like these. So in all these cases, your force is constant. It is not depending upon X, Y, Z, right?
Yes,
But
sir.
but let's say that your force is 3x plus 2y plus 5, let's say something like this, right? So now you can see that your force is dependent upon x, y, and z, which means that
Yes, sir.
f is constant or variable.
Yes, sir.
Yeah, what is the force that I'm asking? A constant one or variable one?
Sir, it is variable.
Variable, because let me write it clearly. So because f is 3xi plus 2yj plus 5k. So if I change x, if I change y, if I change z, then my force will change. So force is dependent upon x, y, z, right? In here, force is not dependent upon x, y, z. So that's why it is constant, right? But in here, force is dependent upon x, y, and z. So this is why it is called a variable. So this is a variable force. Understood?
Yes, sir.
So if I write f to be, let's say, 4x squared plus y squared, then this force is variable force, right?
Yes, sir.
So in the next part, we understood that depending upon the nature of force, right? So depending upon the nature of force, whether this is constant, whether this is variable one. So we have two definitions of work done. So for the constant and uniform one, you already know the work done. That is the scalar product of this force and this displacement, right?
Yes, sir.
But work done for the variable force is defined like this, right? So you have these 2 points. Let me write it as right. So this is S1 point and S2 point, right? So let's say if an object, so this is a one-dimensional force, right? It is only dependent upon x. So let's say you have a variable force, right? So in that
Yes,
case,
sir.
your work done would be defined like understood.
Yes, sir.
Okay, so you are not noting it down. So please note down this part. This is important, right? Please note down this part.
Okay, sir. Fine, sir.
Finished. Good. So we did this problem, right? So can you do this problem? Force is defined like this, working in an object, and it displaces the object from 1 meter to 3 meter. So you have to find the work done. Please do this question.
Okay, sir.
And if you face any problem, so we will discuss this question. So now you
Okay,
see,
sir.
yeah, now you see that force is variable one, right?
Yes, sir.
Okay,
Sir, we should use a degradation, right?
yeah, the second definition, right? So in the integration method that you are saying, yes.
Yes, sir.
And what is the dimension of this force? Can you tell me?
Sir, don't know.
So it is only dependent upon x. So this is in one dimension, right?
Sir, please can you tell again?
Yeah. So F is only dependent upon x. So which means that this is a one dimensional force, right?
Okay, sir. Sir, what is D? What is S?
What is oh, so whenever we have you forgotten the integration? So this is dx, the variable with respect to you are calculating the integral. So remember we did this kind of integral, right? So y dx, this dx is the integral with respect to you are taking the integral. So let's say if you have a function which is x square and you are taking the integral with respect to x, then you write this dx. This dx is
Yes,
small.
sir.
This dx is a small change in x, right?
Yes,
So
sir.
remember the differentiation. In differentiation, we had dy by dx, right? So
Yes, sir.
we did the differentiation of y with respect to
X.
x. So that is why we wrote dx. So similarly, we are doing the integration with respect to dx, right? So
Yes.
in here, your ds, this is a vector, right? So
Yes, sir.
the object is moving in the x direction. So this would be, let me write it for you that this would be x1, x2, and force is minus k x square, and direction is I hat, right?
Yes, sir.
Similarly, ds is dx I hat. So I would be I dot I would be 1, so you will get x1 to x2 minus k by x square dx. This is the integral that you have to solve, right?
Yes,
And
sir.
you know that what is the limit of this x1 and x2. So x1
Yes,
is
sir.
1, x2 is 3.
3.
So your
Yes, sir.
integral is 1 to 3 minus k by x square dx. K is constant and you have to do this integral. Please do this, and whenever you are stuck at some point, then we can discuss.
Okay, sir.
Yes, found the answer or stuck at some point? Okay.
Sir, I'm not getting anything.
Okay, so you did all the questions, so let us understand this question. So work done is 1 to 3 FDX, right?
Yes, sir.
And what do we know this x and dx integral? What is this?
Sir, x n plus 1 by n plus 1.
Right, so we have this minus k is constant, so it is taken outside, right? So this would be 1 to 3, 1 over x square. And this is x to the power minus 2, right? So x to the
Yes,
power
sir.
minus 2 would be how much? X minus 2 plus 1 minus 2 plus 1. So this is x minus 1 and minus 1, right? So x minus 1 and minus 1. And the limit is 3 to 1, right?
Yes, sir.
So now we take this minus 1 outside. This is a constant one, right? This is not a function. So minus 1 we take outside. So this is minus 1 minus 1. So plus k, right?
Yes,
And
sir.
x minus 1, x to the power minus 1 is how much? 1 by x, right?
Yes, sir.
So now if we have this integral, then we have to put the limits of this integral, right?
Yes,
So,
sir.
so in the integration first, which limit do we put?
Upper.
Upper limit, right? So function is 1 by x, so 1 by 3. And then we put the lower limit, 1 by 1. So this would be 1 by 3 minus 1. So this would be minus 2 by 3. So minus 2k by 3. This would be the work done. Understood?
Yes, sir.
So please note down from here, right? So this much we did in the previous class. Okay, we revised that. So, okay. And in tomorrow's class, I will go ahead, right? Whether the rest of the people join or not, because then we'll be stuck at one point. So in tomorrow's class,
Yes, sir.
yeah, in tomorrow's class we'll go ahead.
Finish, sir.
Finished already. Good. So this part also
Yes, sir.
good. So now the next thing was that we understood that if we have a constant force, then work done would be F dot ds. If we have a variable force, then work done would be integral of F ds, right? Now
Yes, sir.
there is a graphical method of calculating the work done. So remember in the VT graph, so when we were doing the motion in one dimension, so motion in one dimension, we had this velocity time graph, right? And
Yes, sir.
let's say this was the graph. So when we calculated the area under the integral, so what was this? Can you remember? Do you remember?
Sorry, sir.
Yeah. So area and so this is the graph of the velocity time graph, right?
Yes,
So,
sir.
so this is the behavior of velocity and time graph. And when we calculated the area under this graph, so what was the thing that we said?
Sir, area of trapezium.
Yeah, area of trapezium. So what was this thing? What was the physical quantity? B into T. What is this physical quantity?
Physical quantity.
Yeah. So when we were doing the graphical solution of the equations of motion, right? So when we were doing the graphical derivation, so what was this velocity? What is this velocity into time? What is this? Speed into time. What is this?
Speed into time. Distance.
Distance, right? So this is what we call the area under the velocity time graph was distance, right? So let me go back to this part and show you. So free fall. After free fall, right. So where is yeah? So in the velocity time graph, when we calculated the area, where is the area? Okay, yeah, in here. So area under velocity time graph, what did we write? That is display distance, right?
Yes, sir.
And that we called the area of trapezium. So then we got this distance, which was this. Understood?
Yes, sir.
So the area under velocity time graph will give you distance. Similarly, the area under the force and distance graph. So area under this force and distance graph will give you work done because F into X is how much work done, right?
Yes, sir.
Okay, so this up to this point we did in the previous class, right? So in tomorrow's class, we'll continue from here. We'll do a question from the graphical part, and then we have finished this work. Then what is the physical quantity that is left?
Sir, at work energy.
Energy, right? So in tomorrow's class, we'll understand about energy and especially about kinetic energy and potential energy. And then we will be left with this power. So then we will do this definition of energy and power, and then we will understand understand about the collision. So then this chapter will be over. Okay.
Yes, sir.
Okay. So we'll stop